Okay, guys. So you wanted to do 15A, which says use the table of Laplace transforms and the results of exercise 13 to find the Laplace transforms of, well, in this case, just sine of omega t over t with omega bigger than 0. And then if you look at exercise 13, it says suppose that f is of piecewise continuous and of exponential order, and that blah, blah, blah. Show that the Laplace transform of f of t over t is equal to the integral from s to infinity of f of r dr. Okay, so what that comes down to is, first things first, I need to check what situation I'm in. So I'm looking at this thing, and I'm thinking to myself, all right, that needs to be piecewise continuous, which I think it is. It needs to be of exponential order, which if you go check out the definition or the video on exponential order, this thing is. And then I need the limit t tending to 0 from the positive side exists. And I remember from Calc 1 that the limit h tending to 0 of sine of h over h goes to 1. So specifically, that means it exists. Okay, so I'm good with check, check, and check on items. And then I need to, all right, I need to see if this thing fits into that. So in order to fit this thing into that, what I'm trying to do is I'm trying to take the Laplace transform of sine of omega t over t, right? That's what the problem told me to do. And so if I look at this, I'm thinking to myself, this top bit is the f of t in the theorem, and this bottom bit is t in the theorem. You guys see that? And this is the L. I can't draw their funky L. Right? Okay, so what the theorem says is that, aha, taking this, I get the integral from s to infinity of, and then here I need capital F. But capital F is related to lowercase f in that it's the Laplace transform. So I have the Laplace transform of lowercase f of t. Whoops. And then this thing says dr, right? And so this is me thinking this is going to be the Laplace, and I'm going to put an r in instead of an s. Just because. Like, there's no reason that it has to take you to magic S land. It can certainly take you to magic R land, and that's totally fine. So then you need to go get your Laplace transform table. I happen to have mine right here. And I need the sine of omega t table, part of the table. So now this is going to be the integral from s to infinity of omega over something squared plus omega squared dr. And then the something is that normally here there's an s, but in my case right now I have an r because I'm evaluating the Laplace transform in r. Okay, so I got this far. Oops. And now I need to actually integrate that thing. And that's rough, because I think I have to remember how, what, oh no. Okay, so it's probably an arctangent. I have to do a little fiddling with it to see that. So what I'm gonna do is I'm gonna say, all right, I'm gonna take this thing, right, this thing, and I'm gonna multiply top and bottom by 1 over omega and whoops, I need to multiply by 1 over omega squared on top and bottom. And the reason I need omega squared is that I'm trying to get, well, let me maybe finish writing and then talk. Okay, so the reason I'm writing omega squared is that I'm looking at this and I'm figuring that's like a 1 over 1 plus x squared kind of thing. And that under anti-differentiation goes to arctangent, right? Hopefully that's familiar. So I'm multiplying by 1 over omega squared in order to get that kind of form where I have 1 over 1 plus some variable squared. And I'll have to do a u substitution to get there. So next step, I've got a 1 over w out front. That's this w from here and the 1 over w. And then I have the integral from s to infinity of 1 over r squared over w squared plus 1. And I guess I may as well square the 1. Oh, I guess it's not squared in the thing. All right. And then that's dr still. Okay, and now I'm going to make a u substitution. So my u substitution in the margin is going to be u is r over w, and then du is 1 over w dr. And so when I do that u substitution, there's my du. So I have the integral from somewhere to somewhere, right, of 1 over 1 plus u squared. I guess if I was being totally honest, I'd write that in the other order. I have u squared plus 1 du. And then I need to decide on bounds. So if r, right, these bounds here are in r's. So if r is s, then u is s over w. And if r is s, then, or sorry, if r is infinity rather, then u is infinity over w. And they told me that w is strictly bigger than 0, so I can divide by it. Well, I'm still going to get infinity out of that. Oops, wrong way. Okay, so next thing, and I'm going to go over here so I have some more room. So I have the arctangent of u evaluated from s over w to infinity, right? Okay. Now I need to know what the, so, all right. So that's going to be equal to the arctangent of infinity minus the arctangent of s over w. And then the arctangent of infinity, so arctangent is a function that looks like this. And it has this horizontal asymptote. So the limit as it goes to infinity is the value of that asymptote on the tangent function, which is pi over 2. So this is pi over 2 minus the arctangent of s over w. And let's go check our, okay, so they asked me for a Laplace transform, and the way I got there was I applied this. So the Laplace transform of a function over a value t is the antiderivative of the Laplace transform of that function. So I Laplace transformed sine. I got this thing. I did a little calculus to find the antiderivative. And then after I found the antiderivative, I evaluated on the limits, and I got this thing. And that, my friends, is how you do that. Okay, so upon further investigation, I went and looked in the back of the book because what the hell, I'm bored, I'm at home, I got nothing else to do. And I know you guys are probably looking there too. And they have that this is arctangent of W over S, which seems super goddamn surprising and until you spend a second with a triangle. There's this kind of, so how about this? Here's a triangle. That's a bullshit triangle, Joe. What are you doing? You should be ashamed of yourself. Okay, so let's see. Do I have a line? Line. Oops. Click, point. Why is it? Oh, my line's white, because of course it is. Okay. Line, line, line. Everyone recognizes that this makes a triangle. I'm going to suppose that side is 1 and this side is x. And then that makes this thing here the arc whose tangent is, let's see, opposite over adjacent, x. Yes? Okay. Cool thing. Add a line here and a line, oops, that's not going to work. And a line like so. And then notice a thing about this arc here. That's the arc whose tangent is 1 over x. See what they added to? So there's this kind of funky fact that apparently your book made use of, which is that the arctangent of x plus the arctangent of 1 over x, they add to pi over 2. And so while I ended up with, oops, let me see if I can, it's real weird that the controls on this whiteboard are backwards. Okay, so while they ended up with pi over 2, or while I ended up with pi over 2 minus arctangent of, let's think about this thing as x, they just ended up with the arctangent of 1 over x, right? The thing flipped over. So they just used this trig identity to rearrange. Frankly, I think they cheated, but there is a certain elegance to this thing. It is actually a lot better. And so in the end, what we have, right, is that the Laplace transform of sine of omega t over t is the arctangent of W over S. And there, ladies and gentlemen, you have it checked in the back of the book even. Haha.